Hi everyone. Sorry I couldn't be there with you today, but this lesson is on the graph translation theorem, which you actually talked a little bit about last year. I think you only talked about it probably in relation to quadratics, but it's not too difficult to wrap your head around. One little tricky piece, but should be okay. So let's start with definition of a translation. Translation, if you remember from geometry, is any type of movement where you're just sliding something around. Okay, you're not changing the shape or the size of the graph, you're just moving it. Okay, you're just picking it up and sliding it where you want it to go. Okay, so this is an important note, and I kind of just mentioned that. But under a translation, graphs are always congruent. So we're not changing size or shape, we're just moving the location. So when we're doing translations, mathematically, what we're actually doing is taking this x, y, and adding or subtracting from those coordinates. And we use our old friends h and k here to represent whatever we're adding or subtracting. Okay. So addition in a rule is going to make us move to the right. Subtraction is going to make us move to the left. Or in terms of the y, addition would make us move up and subtraction would make us move down. So that covers all four of these, right? And so what this rule is really saying is that we're taking the coordinate x, y, and translating it to this new location where we're adding this to x and adding this to y. Okay? This rule thing is going to be really important. I'm going to refer to it several more times throughout our lesson because if you can get back to the rule, I feel like everything else kind of falls into place if you can think about what the rule is for what's happening. All right, but that'll come later. Let's look at example 1. This one's pretty easy. So under a translation, the image of 0, 0 is 7, 8. So that means that I took 0, 0 and did a translation and it turned into the coordinate 7, 8. So what must have happened to each of these points to turn into a 7 and an 8? Well, our rule would look like this. To go from 0 to 7, we must have added 7, right? And to go from 0 to 8, we must have added 8. So this is our rule. Okay, that one was really easy because they started us with 0, 0, but really with any coordinate, we should have been able to say what did they add or subtract to each one. So then find the image of 6, negative 10 under this translation. Well, this is how we perform our translation. We're going to take the x value of 6 and add 7 to it to get 13. And we're going to take the y value of negative 10 and add 8. And we end up with negative 2. Put these two things together in a coordinate, and this would be the new coordinate. This is where this point would go to if we did this translation. So now I want to know what movement just happened. What did we just do? If we went from 6, negative 10 to 13, negative 2, where did we move to? Well, remember, x is always going to control left to right. All right, and maybe I'll write that up here with the rule. X is always controlling left to right. Y is always controlling up and down. Okay, to the right is positive, to the left is negative. You know this if you know what a graph looks like, right? Up is positive, down is negative. So looking at this, x plus 7, that means we must have moved to the right by 7. And then y plus 8 means that we must have moved up by 8. Okay, that's where this translation would move us to. So that brings us to really the biggest topic of this lesson is what's called the graph translation theorem. So take a second and copy this theorem down. And if I don't give you enough time here, feel free to pause the video so that you can write it in. But it says that if you're performing a translation, and this is the rule for your translation, replace the x with x minus h and the y with y minus k. Now something crazy just happened, right? Because this was a plus h, but now it's a minus. And this was a plus k, but now it's a minus, okay? When you're doing these things and you're writing equations, okay, the equation is always backwards from the rule. And I'm going to do my best to give you just sort of a quick overview. I mean, this is kind of a complicated concept, but I'm going to kind of try to show you why this is the way it is. Okay, you're welcome to write this down if you want to, or you don't have to. Let's take the graph of y equals x squared. Oh, I made that a little wide, but that's okay. So this is y equals x squared, okay? And let's just pick a point that we know would be on this graph. So like 2 comma 4 is on y equals x squared. Well, if we took that graph, and I'm going to look for a different color here, if we took that graph and shifted it to the right by 5, okay, I moved to the right by 5. Now my parabola would be over here, okay? So we went 5 spaces this way. And this point, 2 comma 4, if I moved it over, if I move this over by 5, would now be at 7 comma 4. So if I want to come up with an equation for this purple parabola, I need an equation that when I plug in a 7, it's going to spit out 4 as an answer because the 7 needs to be matched up with the 4. Well, if I look at what my equation used to be, y equals x squared, and I try to do y equals x plus 5 squared, that means I would be taking the 7 and adding 5, which is 12, and then 12 squared is 144. That's not anywhere close to where my answer is supposed to be. So this does not work. But if I go x minus 5 squared, and I plug in that 7, that's going to have me doing 7 minus 5, which is 2. And so really what I'm doing is going back to this original point. I'm taking that 7 and turning it back into what it was on the parent function before I square it, and I get 4. Okay, so that keeps my y where it's supposed to be. Okay, so it's kind of like you're compensating. It's like you're compensating for something that's been done to the x. We shifted the x's over by 5, so now we need to imagine what were they before I apply all of my function rules to it. Okay, that's kind of a real basic overview of why this happens, but really this concept's going to come up quite a bit this year. You need to just get used to the fact that if your rule looks like this, in the equation it's going to be opposite. Okay. So if I look at example 2, write an equation for the graph of y equals absolute value of x under this translation. So this is your rule right here. But when I go to put this stuff into the equation, it's going to look opposite from this. So instead of y here, I'm going to put a y plus 7. Okay? And instead of absolute value of x, I'm replacing that x with x minus 4. Okay, notice both of those are opposite from what they were up here. Okay. Now, I'm gonna make sure you believe me on this in just a second, but let's talk about this for a minute. This x plus 4 would have me moving to the right, and this y minus 7 would have me moving down. So I would expect when I graph this equation that it looks just like this one, except it's been moved to the right and down. Okay, so I'm going to head over to Desmos, and we're going to take a look at that. So here's my parent function. Nope, absolute value of x. Okay, that's the original function. Here's my new function that we just wrote down. Y plus 7 equals absolute value of x minus 4. And you can see, and I keep trying to point to the screen, but you guys can't see me pointing, that this red graph has shifted over to the right, whoa, zoomed it out a little bit, over to the right by 4 and down by 7, okay, which is exactly what we wanted to have happen. Move to the right 4 and down 7, okay? So if you didn't believe me before about the opposite thing, about the, putting in a plus when you really want a minus and things like that, hopefully that convinced you. Okay, let's keep going. We have a couple more examples here. Example 3 gives me a parent function here, y equals x squared, and then gives me a verbal description of what I want to have happen. What I would do is I would take that description and write a rule. I would always go back to the rule. Okay? So to go up 2, that's going to be a plus 2 on the y, right? And 3 to the left, that's going to be a minus 3 because it's to the left on x. So my rule would look like this. xy goes to x minus 3, comma, y plus 2. Start with that, because once you have that written out, we know exactly what we need to put in the equation. It's the opposite of what you see here. The equation then is going to start with y minus 2, and again, that's opposite of this, equals x plus 3 squared. Okay? So the equation and the rule are opposites of each other. Okay? And the rule is always a direct reflection of what's actually happening. The equation is where you have to do all that compensating. So you do everything backwards. Okay? Notice that I put this x plus 3 in parentheses. That's because we wanted to make sure that whatever we're doing to the x is being done directly to the x. Okay? So before anything gets squared, we don't want to put that plus 3 on the outside here. We want to attach it directly to the x and then do whatever else is happening in my function. So a lot of the times when you do things to x, you're going to need parentheses. Okay, one more quick one. Sketch a graph of this function, and they've given us an equation. Okay. So once again, before I start anything, I would start with a rule. And we're kind of going backwards here. I started with an equation this time, which remember, everything in the equation is backwards. So in my rule, where I see x plus 3 here, my rule would be doing x minus 3. And where I see y minus 2, my rule is going to do y plus 2. Things are like rebellious children. They do the opposite of what you tell them to. Okay, now that I have my rule, I would think about what this is doing to the graph. X minus 3 is moving me to the left by 3. Y plus 2 is moving me up by 2. Okay, now before we can draw a graph, we need to think about what the parent function of this one is. And for finding a parent function, I kind of imagine we're getting rid of all of those transformations and look at what's left. We have y equals 1 over x squared. So we need to start with that graph, right? At least in our minds. And sometimes what I do is just kind of sketch it maybe lightly in pencil first. Is that my original graph looks like this. It's one of those side-by-side hyperbolas, right? Now if I want to shift it to the left 3 and up by 2, I'm going to go ahead and move the origin of my graph. So I'm going to go to the left 3 and up by 2. That would maybe be here. I guess I should actually left 3, up by 2. And I'm going to picture that this is where my new axes are. Okay, really what I did was I translated the origin of the graph. I translated this point right here before I actually drew anything. And now all I need to do is recreate this picture, but on my quote-unquote new coordinate plane. Okay, so my picture is going to look like this. Whoops, it shouldn't have crossed that purple line. It's just a slip of my pen. And there. Okay. And that's what our new graph would look like. Okay. Okay. So that's really it for this lesson. Your homework is a worksheet in your packet. It just says worksheet 3.2. I think what I will do is post another real short video that is just a tutorial. I'll run through the first problem on your homework so you have an idea of what it's asking you to do. On Monday, you do have a quiz, a very short quiz that looks just like that homework assignment. Okay? But we'll make sure to go over that homework assignment plenty before you take the quiz. But if you are confused on the homework, you'll want to check out that other video. Okay? Have a great day and have a good weekend.